Hello everyone. In this video series, we're going to analyze 500 MCAT Physics questions from McGraw-Hill Education. MCAT requires constant study and lots of practice. So that's what we're going to do here by analyzing the questions deeply. And those are the topics of the questions that we are going to analyze in part 1, part 2, and part 3. And their subchapters, part 4 and part 5. This video is about part 1, chapter 1, translational motion. In this video, we are going to analyze 38 questions. Question number 1. Which of the following equations describing acceleration A, displacement s, time t, and velocity v for a moving object could be dimensionally correct? For this question, we're going to do dimensional analysis. So we need to know what each item here is measured by. So the unit of acceleration, as we know, is meter over second squared. And the unit of displacement, which is s, is meter. And unit of time is measured by the second, and the unit of the velocity is meter over second. Now we're going to substitute these units into equation to see whether this equation is true or not. In option A, we have acceleration, which is meter over second squared, equals to velocity times time cubed. Velocity equals to meter over second, and time is equal to second, and we have cubed here, and displacement s is equal to meter, and we have square here, so meter squared. Now if we do necessary simplifications, so this is going to be second squared, and meter divided by meter squared is 1 over meter. So second squared over meter squared is left on the right side, and on the left side we have meter over second squared, which are not equal to each other. Now let's see B. Velocity is meter over second, acceleration is meter over second squared, times displacement is meter, and we have t squared, which is second squared. And here we obtain meter squared over second squared on the right hand side over second squared. You can think this is over 1, and if you do keep change flip, you get meter squared over second to the 4th power, which is not equal to meter over second, so B is not correct either. Here we have velocity squared, which is meter over second the quantity squared. We have acceleration, which is meter over second squared, times displacement, which is meter. And if we take the second power of this fraction, we get meter squared over second squared equals to meter times meter is meter squared over second squared. So this equation is true because it is identically same on the left and the right. So the answer is C. Question number 2. Which of the 4 graphs below best represents a graph of y as a function of x squared? We know that x squared is the parabola, and parabola is like this. This is y equals to x squared, and this is the right side of the parabola here, so answer B is correct. Here, if you don't remember that x squared is the parabola, then you can do table analysis, like y equals to x squared. So when x is, let's say, 0, y equals to x squared is equal to 0. When x is equal to, let's say, 2, y is equal to 4. So we are squaring to find the value of y. X is 10, y is 100. So we see that y value is always the square of the x value, which means the graph is increasing always. Here the graph is decreasing. Here at some point the graph is decreasing, and the graph is decreasing here. So B is correct. If you know some parent functions by heart, it's going to be very helpful, like parabola, which is x squared, y equals the x squared. If you know square root of x, it is also helpful. This is decaying exponential function like e to the negative x, and this is the equation of the quarter circle. Let's see question number 3. On a graph that has a quantity measured in newtons on the y-axis and a quantity measured in meters on the x-axis, what units would identify the quantity associated with the slope and with the area? We know that slope formula is delta y over delta x, total change in y over total change in x. So y-axis over x-axis will give us the slope. And the area formula for general polygons are base times height. So let's analyze this question on the xy plane. So on the y-axis we have Newton, measured by Newton, and on the x-axis it is measured by the meters. So the slope of any line on this graph will be Newton over meters. Change in y, which is measured in Newton, change in x, which is the units of meter. So slope will be newtons over meter, and the area in general will be base times height, which will be Newton times meter. So answer A is correct. Let's check question number 4. Work is determined by multiplying force time distance. 1 joule of work is the equivalent of 1 Newton of force multiplied by 1 meter. Which of the following is equivalent to 1 joule? We were given the general formula for work, which is work is force times distance. So you don't need to know this by heart, it is given in the question. And you were also given the definition of 1 joule. 1 joule by definition is 1 Newton times by 1 meter. So 1 joule is equal to 1 Newton times 1 meter, which is Newton times meter will give you the unit of joule. Now we're going to analyze the options. So force is given in Newton, everything here, but here it is given in centimeters. So we're going to convert this into meters. So 200 centimeters is equal to 2 meters. 20 centimeters is equal to 0.2 meters. 2 centimeters is equal to 0.02 meters. And 0.2 centimeters is equal to 0.002 meters. Now we're going to multiply them by the Newton to get the unit joule. And specifically, we are searching for 1 joule, the answer. So 5 times 2 is 10. So this is 10 joules. That's not what we are looking for. 5 times 0.2 is equal to 1.0. So this is exactly what we were looking for. And the others are not 1. Question number 5. Quantities in everyday applications often have the prefixes mega and micro. How many micrometers, μm, sometimes called microns, are equivalent to 1 megameter, capital MM? Here we are going to convert 1 micrometer into 1 megameter. It is known that 1 micrometer is 1 millionth of a meter. So 10 to the 1 times 10 to the negative 6 meter is equal to 1 micron, 1 μm. And megameter is 1 million times bigger than meter. So 1 times 10 to the 6 meter is equal to 1 megameter. Now we're going to convert 1 micrometer or 1 micron into 1 megameter. So from 1 micrometer to 1 meter, we have 1 times 10 to the 6. We have to go 1 times 10 to the 6 unit away. And from meter to megameter, we also have to travel 1 times 10 to the 6 unit away. and together it's gonna be 1 times 10 to the 12 units times more. C is the answer. Or you can go very thorough dimensional analysis for this question. This was just intuitively and practically. You could also answer this question like 1 times 10 to the 6 micron over 1 meter, because we know that they are equal, times 1 times 10 to the 6 meter is equal to 1 megameter. We know that they are equal as well. Now we're going to simplify this. So here we would like to obtain micrometer over megameter. So here meter cancels meter, and the numbers will be 1 times 10 to the 6 times 1 times 10 to the 6 will be 1 times 10 to the 12th over 1, and micron over megameter. Question number 6. If quantity X is measured in kilograms, quantity Y is measured in meters per second, and quantity Z is measured in meters. Determine the units for the calculated quantity. So we're going to substitute the units here. So we were given kilogram for X, kilogram. For Y, we were given meter per second. So meter per second, and we have squared here, divided by Z, and Z is measured in meters. Now we're going to obtain kilogram times, if we take the second power of this fraction, meter squared over second squared divided by meter. So this is going to be one fraction over another fraction, which is going to be keep change flip. So it's going to be kilogram over meter squared divided by meter times second squared. And here one factor of meter squared is gone. So kilogram times meter over second squared. So the answer is kilogram times meter over second squared. This is A. Let's go to question number 7. If quantity X is measured in newtons and quantity Y is measured in kilogram over meter, determine the units on the calculated quantity. So first you need to know Newton by definition. Newton is equal to kilogram times meter over second squared, which is like acceleration times the weight, kilogram. So Newton is kilogram times meter over second squared. And now we were given X in Newton. Instead of Newton, we're going to use kilogram times meter over second squared, because in the options we don't have in terms of Newton. So square root of kilogram times meter over second squared instead of X, and instead of Y we're going to write kilogram over meter. Now one fraction over another fraction, we're going to do keep change flip. So kilogram times meter over second squared times meter over kilogram, and we have radical sign here. So here kilogram cancels kilogram, and we have meter squared over second squared, and that goes outside of the radical sign as meter over second if you take the square root of both numerator and denominator. So the answer is D. Let's go to question number 8. Question number 8. The equation for the ideal gas law is P times V equals to N times RT, where P is the pressure, V is the volume, N is the number of moles of gas, R is the ideal gas constant, and T is temperature. Which of the 4 graphs below best represents the plot of pressure versus volume, where N, R, and T are constant? Since we are checking the relationship between pressure and volume, where all others are constant, Now we're going to solve for pressure here or volume for here. So in our equation we have PV equals to nRT. Let's solve for P to see the relation between P and V better. So here P will be equal to, if we divide both sides on V, nRT over V. Now we can see the relation between P and V. P and V are inversely proportioned here because one is on the numerator, one is on the denominator. Or you can think like this. This is constant number, and as V is getting bigger, this constant number, let's say it's 10, and V is getting bigger and bigger, and still 10 is divided by that number. So we obtain smaller and smaller number. So as V is getting bigger and bigger, the value of P is getting smaller and smaller. So they are inversely proportioned. So graph A is showing the inverse proportion here because as V is getting bigger on the x-axis going to the right, the value of P is getting smaller. As volume is getting bigger, pressure is getting smaller. So since they are inversely proportioned, or as V is getting bigger, P is getting smaller, that's the graph of A, because as V is getting bigger going through right on the x-axis, P is getting smaller, the Y value. Here as V is getting bigger, P is also getting bigger. Here as V is getting bigger, P is constant up to some point and then getting smaller. Here as V is getting bigger, P is getting, but this is limited function. Here the function has no boundaries. So A is correct.